And hello friends, welcome back. So moving on, we just found out how to do this integration, okay, with this temperature profile. Now, of course, the most important thing about temperature profile is that actually we want to find out is the heat flux. Okay, we want to find out heat flux. All right. Okay, so the key to finding out heat flux is of course with this data prime 0. Okay, the temperature profile is interesting at all, but it's not as important as say the heat flux. Okay, and this thing here is a little bit tedious to derive. I mean, it's possible, and you can do it numerically. However you want it. Now you can solve this numerically. Over here, you solve this numerically, and that's okay. That's actually what we want to do. But we can solve this numerically using MATLAB, Python, whatever. But I'm not going to discuss that. This is just the form that you can go and try on your own. But the heat flux is what we are interested in. Okay. So remember, heat flux Q double prime equals to minus K partial T partial Y, and we'll need to redo kind of our whole analysis here. Okay, and of course we need to put it at Y equals to 0, right? Y equals to 0. Y equal to 0. That's it. Yes. So again, how are we going to change this? Okay, we'll try to change all of this to theta. Okay, we'll try to change all of this to theta. Again, you do minus TS here, and that should be okay. And after that, we will include the factor of Ts minus T infinity. Okay, so we have a Ts minus T infinity. So this T minus Ts is actually theta times Ts minus T infinity, or divide by Ts minus T infinity. Yeah. Wait, no. What am I saying here? This T minus Ts is theta into Ts T infinity minus Ts rather. Okay, so we'll do that. T infinity minus Ts. Alright. I guess my brain's getting a little tired, so maybe it means I should stop working soon. Take some of that warning sign, Okay. And of course, if we want to have a heat transfer coefficient, H equals to Q double prime over minus T infinity minus Ts. Of course, H is always should be a positive number. So we'll just take the positive part out. Okay, so this is the heat transfer coefficient. I think going from we'll just take out the negative sign. It's that's the idea here. All right, so we have H equals to K del theta del Y at Y equals to 0. So H over K will be this, and the last bit. Okay, the last bit for us will be to include how do I say yes, we'll need to do some change of variables here. Okay, we need to do some change of variable. So this partial theta, partial eta, and then you need to multiply into partial eta, partial y. And if you recall, partial eta, partial y is just eta over y. Okay, so it's just eta over y. What is eta over y? Eta over y is half into, okay, half into square root or something. I can't remember what the square root is. Let's go and find out. Okay, so eta over y is actually half into square root u infinity fraction half square root fraction u infinity over nu x. Okay. Okay, so this is good. And this is actually theta prime 0, right? It's the same thing. It is the same thing. Theta prime at 0. Alright, so what is this over here? This is actually square root of Reynolds number over x. Okay, so we multiply the top and bottom by x, and then we just bring the x out. We should be able to get a Nusselt number. So square, x square, and okay, we'll bring that thing out. So bring out the x squared. We'll bring hx over k, and then we will non-dimensionalize it in there. Square root of rex. Okay. Okay, so now we have a Nusselt number, so to speak. So this x squared came out, and you should sort of have a Nusselt number here, nux. So we need to find this dimensionless heat flux at eta equals 0. Then we will be okay. Now this actually here it looks too complicated, right? I mean, you substitute in here, you'll be absolutely correct. Yeah, you'll be absolutely correct to substitute this wholesale right here. And that's a very inconvenient, impractical expression to use for your Nusselt number. Equals to fraction half times this whole thing. Okay. Okay, so that's what you have. Of course, yeah. Then if I were to bring the half in, okay, yeah, it would really look like the textbook expression. In textbook expression, okay, I'll just bring the half in where the Prandtl number is, because no matter how you do it, is the same expression at the end of the day. Okay, when you take out all these dimensional parameters, all right, in the textbook expression, it will look something like that. Now, getting this whatever is in here. All right, I need to get rid of the theta 0. You know, it's like double work. Yeah, getting this expression here. Getting this expression here. What is the value? What is the value of this whole thing? And what's the value of this whole thing? Okay, the value of this, thankfully, it has been worked out before by Paulhausen. Sorry if I butchered the name. Okay, Paulhausen worked it out. So actually this whole value thing here, what is equals to for Prandtl number more than 0.5, so you need a high Prandtl number thing. So just to give you some idea, okay, okay, let's give it an approximation. Okay, this should be equal to Prandtl to the power of 0.333 or 0.332. Give or take. Okay. Let's put a 0.333 then. Or maybe just 1/3 will do. Fraction 1/3. Okay. Okay. Alright, there you go. For Prandtl number more than 0.5. Okay, for Prandtl number more than 0.5, it is approximately this value. You can use the correlation. Okay. How do you know what has a high or low Prandtl number? Just to give you some intuition, liquid metals. Okay, the Prandtl number of that is less than 0.1 usually. Air, okay, Prandtl number equals to about 0.72, give or take. Okay. Water, let's go. Okay, let's look at the Prandtl number of water. Prandtl number of water is around 1 if I'm not wrong. Varying temperatures. So as a liquid, it's not 1. It's a bit hard to see. Okay, give or take about 20 degrees. Water will have a Prandtl number of 7. Okay, 7. Okay, and if you look at some other oils, they will have a very high Prandtl number. Okay, some transmission fluid or whatever, the oil will have a high Prandtl number. Okay, so basically, what I like to think about, what I like to roughly give an intuition for Prandtl number. Okay, for liquids of similar. Okay, what does the Prandtl number tell us? Okay, Prandtl number says that for liquids of same viscosity, higher Prandtl number means lower liquid conductivity, or more accurately thermal diffusivity. Okay. Okay. Lower thermal diffusivity. Yeah. Okay, we'll just use the word thermal diffusivity here. Okay. Thermal diffusivity. And thermal diffusivity means that usually temperature can flow through the thing well. It feels as if, okay, so for thermal diffusivity, okay, the intuition, okay, high conductivity, high thermal conductivity, it means high thermal diffusivity. Okay, all else constant. So this is just to give you some intuition. Okay, so this correlation actually works for anything except liquid metals most of the time. Air, water, oils, everything else mostly we can follow this. So in the textbook expression, yeah, we can just get this Nusselt number out. Okay, you just copy and paste this 0.332 Prandtl number to the 1/3. Okay, and we are done. We have a Nusselt number expression. Okay, so I think we want to, yeah, we substitute this expression into the Nusselt number expression for this big thing here. We will get this expression. Of course, we want to bring the 0.332 in front so it looks nicer. Okay, and how does this compare to our Reynolds analogy? So if we take a look at our Reynolds analogy, you see that it's actually Reynolds analogy. Yeah, Reynolds analogy is 0.332 square root of Reynolds number to the x. But if we include the change of Prandtl number, at least for Prandtl number higher than 0.5, okay, then we'll have a Prandtl number to the 1/3 here. Okay, so not that difficult. I mean, the final form looks okay. It's just that it's a bit tedious to get here. Otherwise, the concept isn't too difficult to grasp, in my opinion. Okay, so there you go. Okay, let's see how much time we have. Okay, for 4 minutes. All right. Well, in the remaining 4 minutes, I could actually start introducing you to the integral solution. Okay, and that's what we're going to do next, pretty much. Okay, we're going to look at the integral solution to this flat plate boundary layer. Okay, with constant temperature. This is the simplest case. Okay, constant temperature. Okay, so thermal boundary layer equations. Okay, so the whole while we've been doing constant temperature boundary layer, because that's the easiest part. Okay, constant temperature boundary layer, force convection boundary layer. Okay, there'll be other cases as well. For example, if there's a constant heat flux or some other thing, and this is useful to help us to validate any like CFD code or anything, because we know these analytical solutions are pretty accurate, pretty good. So we've developed the thermal boundary layer solution for similarity solution based on Paulhausen's analysis and the approximation used here. It's a good correlation, it works. Okay, so the next part will be integral solutions to thermal boundary layer. Okay, then of course we'll probably want to compare these two. Okay, so yeah, integral solutions from thermal boundary layer, not too much of a problem. All right, of course you can actually integrate this out for NUL as well. NUL equals to 1 over L, integrate from 0 to L dx of this whole thing of NUX, right? And if we were to do the same thing, we'll realize that Prandtl number, if it's a constant Prandtl number, we can just we can take the Prandtl number out, no problem. And a long story short, if Prandtl number is constant, okay, we can take the Prandtl number out, and okay, we will get the same thing we did before for our Reynolds analogy. Oh, why is it doing this? So weird. Oh, there you go. Yeah, if we're gonna do this, this actually just becomes 0.664. Okay, it's the same as before, just like the Reynolds analogy. So I'm not gonna prove it fully here. So I just put 0.664 in front. Okay, REL to the power of half. Power of half. And that's basically it. Okay, I'm not gonna do the proving thing again. It's there. So yeah, next is the thermal boundary layer integral solutions for constant temperature temp flat plate. That's the most basic thing to know. Okay, so that's it. Thanks for watching. We'll see you guys next time, and we'll start looking at integral solutions, or we'll try to look at integral solutions. Okay, see you again. Bye bye.